In this video, we're going to go over water equilibrium. So pure water doesn't conduct electricity. At least you can't detect that it is conductive with a regular conductivity apparatus. However, if you get like a super sensitive meter, you will see just a tiny bit of conductivity being picked up by a super sensitive meter. So if we get some conduction, what on earth is happening here? So if water conducts electricity, then there has to be some ions present. Therefore, we can conclude that water must ionize a small amount. So according to an Arrhenius modified reaction, this is what it would look like. So we have two water molecules reacting together to produce hydronium and hydroxide here. So they've written another reaction below here, but these are both the same reaction. They've just taken these two molecules of water and just put them as one reactant with a 2 coefficient there. Okay. So what this is called when a substance reacts with itself to produce ions, it's called autoionization. Now, if we were to create an equilibrium expression for this, I'm just going to focus on this last reaction here. But if we looked at this, notice that we only have one liquid present in this reaction. So in our equilibrium law expression for the autoionization of water, which is what is happening here, if we wrote it out, so okay, we always do products over reactants. How we would write it out is the equilibrium constant for water, and it gets a special W. So our products are hydronium and hydroxide. Now, since our reactants, we only have one liquid, we do not include that in our equilibrium law expression. So this is the equilibrium law expression for the autoionization of water. Now, this reaction favors the reactants quite considerably. So what that means is you're not going to get a whole lot of hydronium and hydroxide ions. Most of what you're going to have in a glass of water is just regular H2O. Okay? And less than 2 water molecules, just to put it into perspective, but less than 2 water molecules per 1 billion will ionize. So again, writing the equilibrium law expression, and we're using W to mean that this is specifically for water. Okay, it's just going to be hydronium, the concentration of hydronium multiplied by the concentration of hydroxide. Now it says here off to the right that the equilibrium constant for water is 1 times 10 to the power of negative 14, so we need to adjust this so that it's superscript, and you don't have to memorize this constant. You can find it in your data booklet if you go up to page 3. You'll find it right here. Okay, so you do not have to remember the equilibrium constant for the autoionization of water. It's 1 times 10 to the power of negative 14. Remember that equilibrium constants do not have units. So you'll find this page 3 data booklet. And what this incredibly small number tells us, so we know it's a very small number because our exponent is negative. So essentially what that means is you have, like if you wrote this number out normally and not in scientific notation, you would have 0 point and then 13 zeros and then a 1. Okay, so it's a very small number. And this small value for an equilibrium constant for the autoionization of water, that tells us that reactants are heavily favored, which is what this piece of information told us. So because this number is so small, this tells you that the reactants are heavily favored. Now, for all neutral solutions, the concentration of hydronium, which we need to adjust this to make sure the charge is superscript, is going to be equal to the concentration of hydronium. So both will have a concentration of 1 times 10 to the power of -7. So if we wrote this out underneath our equilibrium law expression, what that would look like is our Kw is equal to, so assuming this is for a neutral solution, 1 times 10 to the power of -7 for concentration of hydronium and hydroxide, which would give you, if you multiplied those two numbers together, that would give you 1 times 10 to the power of -14, which is the equilibrium constant for the autoionization of water. Now for acidic solutions, so let's highlight that that was for neutral solutions, but for acidic solutions, you will have a higher concentration of hydronium ions compared to hydroxide ions. Okay, because the more hydronium ions you have, the more acidic something is. The more hydroxide ions you have, the more basic something is. Okay, so we're going to go to an example where we have to use this equilibrium law expression for the autoionization of water here. So it's asking us to calculate the concentration of hydronium ions for a solution of sodium carbonate with a hydroxide ion concentration of 0.25. So let's start off with our equilibrium law expression. Okay, and what I'm going to do is I'm going to work on isolating the concentration of hydronium first. So what I'm going to do, since the concentration of hydronium is being multiplied by the concentration of hydroxide, I'm going to divide by the concentration of hydroxide, and what I do to one side I have to do to the other. So then these cancel out, and what I'll be using here is Kw divided by concentration of hydroxide ions gives us the concentration of hydronium ions. So now at this point, Kw, or the equilibrium law constant for water, is a constant already given to us. So that's that 1 times 10 to the power of -14. So I'm going to plug that in. We were told that the concentration of hydroxide ions is 0.25. So if I put that in my calculator, so 1.0 times, so I'm going second function and then the log button to get the 10 to the power of negative 14. I'm going to hit the right arrow to get out of the exponent and then divide by 0.25. So I get 4 times 10 to the power of negative 14. So that E just means times 10 to the power of. So I'm going to flip this equation around here so that my hydronium is on the left-hand side, and it's just a matter of preference here. Okay, so in terms of significant digits, you don't use constants given to you in your data booklet to determine sig digs. You got to use the numbers given to you in the question. So this number right here has 2 sig digs, so I need to write my final answer in 2 sig digs. And I also need to include units. So that's going to be 4.0 times 10 to the negative 14. Remember, for scientific notation, the sig digs are only counted here. The times 10 to the power of whatever exponent, that's not included in what you're counting for sig digs. And I'm going to go moles per liter. And that's my answer. Okay, example number 2, we need to calculate the hydroxide ion concentration for a solution of hydrochloric acid with a hydronium concentration of 0.038. So we're going to do a similar thing. We're going to start off with Kw is equal to concentration of hydronium multiplied by concentration of hydroxide. Since we were asked to calculate the concentration of hydroxide, that means I need to isolate it. So I'm going to divide by hydronium. So then I'm going to get, actually, I'm going to put my hydroxide on the left-hand side. So Kw is equal to, concentration of hydroxide is equal to Kw divided by hydronium. And now we just plug in our numbers. So 1 times 10 to the power of negative 14 divided by 0.38. So 1 times 10 to the power of negative 14 divided by 0.038, that's going to give me 2.6315, goes on forever, times 10 to the power of negative 13. So oftentimes people will forget the times by 10 to the power of whatever after the ... so make sure to watch out for that. And this is moles per liter. So this value has 2 sig digs, so I got to put my number in 2 sig digs. So then if I count from the left, 1, 2, there's my cutoff line. So 2.6 times 10 to the power of, that's negative 13 moles per liter. That would be the concentration of hydroxide. So basically what this is saying is you can use the equilibrium law expression for water to find either the concentration of hydronium if you have the concentration of hydroxide, or you can use the equilibrium law expression for the autoionization of water to find the concentration of hydroxide if you already have the concentration of hydronium. One last thing is that this formula is not given to you in the data booklet. So the constant for Kw, that is given to you on page 3 of the data booklet. However, this formula is not given, so I highly recommend that you memorize it.